So we're going to be talking about things like molar mass, percent composition, empirical formulas, and molecular formulas. So you can think about really there's two ways of counting that we deal with when we're looking at chemicals. One is the mass, the total amount of all stuff, protons, neutrons, and electrons. And the second is moles, the total number of things regardless of the mass per thing. So why do we have two ways of counting? It's the same things. Why do we have these two different bookkeeping systems to keep track? And the answer is we can't count number of atoms. What we'd like to do is just deal with the number of atoms, because we have chemical reactions. The chemical reactions depend on the number of atoms that there are. But we can measure the mass by observing the effect of forces. Putting everything in a beaker, putting it on a scale, there we go. We know what the mass of this is. So that's why we have two different ways of measures. If we know the mass per thing, then we can find the number of things that we know the mass. So this quantity, the mass per thing, the mass per compound, is what we need to go back and forth between things we can measure and then the chemical reactions that occur. So calculating the molar mass, this is something that should be pretty straightforward for people here. All we do is total up the mass per atom in the molecule. And something that, just to remind you that we use the isotopically weighted masses. We don't use the mass of just carbon-12 or just carbon-13. We don't even worry about whether we have carbon-12 or carbon-13, except in very rare circumstances where you maybe like buy just an isotope. Because when we have like 10 to the 20th atoms, which would be like anything more than a milligram or so, we have a mix of isomers. And the mix of isomers is generally the same everywhere. We've talked about a few weird examples. You can separate one isotope from the other, but if you're just grabbing stuff that you get from a chemical company, it's going to be the same isotopic mixture that you see everywhere else on Earth. So what's the molar mass of potassium carbonate? Well, let's dive in and see. So all we do is we get a periodic table and we start looking things up. So the molar mass of potassium carbonate, we look at, I like red. Switches back from the default. Red is easier to see, I think. Okay, so the molar mass of K2CO3 is just going to be 2 times 39.10, which is the molar mass of potassium, plus 12.01 molar mass of carbon, plus 3 times 16.00, and that gives us 138.21. And what is this? This is the grams of K2CO3 per mole of K2CO3. And I like writing it like this when I've got a bunch of molar masses that I have. So it's very clear that this is a conversion factor. A molar mass is a conversion factor between grams of a thing and moles of a thing. Okay, so that should be pretty straightforward. You got your periodic table, you could add everything up. One thing to be aware of is, of course, significant digits. Notice that the top has, each of these individual components has 2 significant digits, but since we're adding it up, we actually have, each of these has 4 significant digits. It has 2 significant digits after the decimal place. Once we add it all together, we actually have 5 significant digits because now we have 3 digits, all of which are significant in front of the decimal point, and 2 significant digits after the decimal point. Okay, so that's the molar mass. And that's the key, because if we have the molar mass, we have the mass per thing, and we can convert from masses to things.